Hello friends, welcome back to my YouTube channel. This will be 33rd part of my discussion on distillation, and since last few videos I have been talking about the McApthily method. Continuing with that, today I will be discussing minimum reflux ratio and how it is uh, treated in the McApthily method. So let us start the discussion. To begin with, let us understand how the column is operated under total reflux. I have discussed about this topic in my previous video. Please, I'm giving link to that video in the description section. You please watch that video. Over here, let me tell you briefly how the column operates under total reflux. So you have the column and then the trays in it. Feed is given to the column and then it is stopped. Enough feed is given to the column. Then all of the liquid is boiled in the reboiler. All of the liquid is boiled in the reboiler over here. And then the resulting vapors, they are admitted into the column at the bottom. And those vapors will be rising to the top where they will be removed and taken to the condenser. All of the vapors will be condensed in the condenser and all of the condensate will be sent back to the column as reflux. No distillate product is taken. So you have the reflux, all the condensate is going back to the column as reflux. L0 is its molar flow rate, XD is the mole fraction of more volatile component in it. And then after entering the column, it will slow down and join the liquid on the feed plate. The bottom product is also not taken out. And this is how the column is operated under total reflux. So you are not taking distillate. So in this case, distillate is 0. The molar flow rate of distillate is 0. You are not taking out bottom product. So in this case, the molar flow rate of the bottom product is also 0. So what important points you can note for this particular operation? No distillate is taken out. All the condensate is written back to the column as reflux. Reflux ratio is infinite. And how can you understand that? So reflux ratio, it is defined as L0 upon D. And if D is 0, that means R will be infinite. So reflux ratio is infinite. No bottom product is taken out. As I said earlier, W is 0. No bottom product is taken out. Then operating lines, that is operating line for the rectifying section and then for the stripping section. Both of them coincide with the diagonal line. I have discussed about this in detail in my previous video. Stages required for this particular operation are minimum. That means you are able to achieve the desired separation with minimum possible stages. Then reboiler heat duty is maximum because you are boiling all liquid in the reboiler without taking out the bottom product. Therefore, maximum amount of heat is supplied in the reboiler. And that is what we are saying. Reboiler heat duty is maximum. Then when a large or when the maximum quantity of liquid is boiled, the resulting maximum quantity of vapors are to be condensed in the condenser. So maximum amount of heat is to be removed. That's why condenser heat duty is also maximum in this case. Okay, now let us see what happens if the reflux ratio is decreased from its infinite value at the total reflux. So as the reflux ratio is decreased from its infinite value at the total reflux, what happens? Let us understand. We'll understand what happens to the rectifying section line and then what happens to the stripping section line. how their position changes on the XY plot. That is what we are going to understand. To begin with, the rectifying section line on the distribution diagram, what changes occur in it? Its slope decreases. So slope of the rectifying section line in terms of R is given by this equation. Slope is equal to R upon R, R upon R plus 1. And for your understanding, I have chosen some values of R which are decreasing, and then I have calculated the corresponding value of slope. So you can easily observe as the value of R is decreasing, slope is also decreasing. That means the line, the rectifying section line is becoming more horizontal. And at the same time, it is moving towards the equilibrium curve. And this movement is occurring along the Q line, or this movement occurs along the Q line. I will shortly show you how that happens. Then the stripping section line, what happens to the stripping section line on the distribution diagram? Let us understand. The first thing is, stripping section line intersects with the rectifying section line on the Q line. And that's why if the rectifying section line is moving towards the equilibrium curve, the intersection point of the two operating lines, it is also moving towards the equilibrium curve. So as the stripping section line intersects with the rectifying section line on the Q line, the intersection point moves towards the equilibrium curve. In other words, it also moves towards the equilibrium curve. That is, the stripping section line also moves towards the equilibrium curve. And then the distance between the operating lines and the equilibrium curve, it decreases. So if you follow distance between the operating lines and the equilibrium curve along the Q line, then you'll come to know that that distance decreases. So as the two lines become more horizontal, they come closer to the equilibrium curve, the distance between them and the equilibrium curve, it decreases. And this distance is nothing but the magnitude of the driving force for mass transfer. So if the distance is decreasing, that means the magnitude of the driving force for mass transfer also decreases. Okay? So over here we have understood what happens if the reflux ratio is decreased. If the reflux ratio is decreased, slope of the rectifying section line decreases. It becomes more horizontal and it moves towards the equilibrium curve along the Q line. The stripping section line, as intersection of stripping section line and rectifying section line occurs on the Q line, the intersection point moves towards the equilibrium curve. Therefore, the stripping section line also moves towards the equilibrium curve. And in this process, the distance between the operating line and the equilibrium curve along the Q line, it decreases. And this distance is nothing but the magnitude of driving force for mass transfer. That means if the distance is decreasing, the magnitude of driving force is also decreasing. Okay. Now you'll understand this when I show you the distribution diagram. So let us follow all this on this distribution diagram. So you have X plotted on the x-axis. X is mole fraction of the more volatile component in the liquid phase. Then Y is plotted on the y-axis. Y is the mole fraction of the more volatile component in the vapor phase. So you have the diagonal line and then you have the equilibrium curve. So let us first plot the rectifying section line. So it starts at a point on the diagonal which has coordinates of xd, xt. And it has an intercept of xd upon r plus 1 on the y-axis. So you have this rectifying section line. Then Q line, it starts at a point which has coordinates of xf, xf on the diagonal line. And it will, depending on the feed condition, it will be located or it will be positioned in different ways. For example, for partially vaporized feed, it will be having a negative slope and it will look like this, or it will be positioned in this way. So here there is intersection of the rectifying section line with the fade line or the Q line. Then stripping section line, it starts on the diagonal, which has, it starts at a point on the diagonal which has coordinates of xw, xw, and it will start at this point, and then it will pass through the point of intersection of the Q line with the rectifying section line. Okay. So now we are discussing what is happening if the reflux ratio is decreasing. So as understood earlier, if you just first talk about the rectifying section line, its slope is going to decrease and it is going to become more horizontal. And in that process, it will be moving towards the equilibrium curve. Okay, so let us see. Now, when the reflux ratio is decreased, the rectifying section line is moving towards the equilibrium curve. And this moment, the point of intersection is also moving towards the equilibrium curve. Same thing will happen with the rectifying section line. So rectifying section line will also move towards the equilibrium curve. On further decrease in the reflux ratio, the rectifying section line will move closer to the equilibrium curve, and it will be followed by the stripping section line. Okay, so you must have observed, as you are decreasing the reflux ratio, this intersection point is moving towards the equilibrium curve. The two lines are moving towards the equilibrium curve. Okay, so with a decrease in the magnitude of the driving force, so this distance, the distance between the intersection point and the equilibrium curve, it is decreasing with the reflux ratio. And this distance is the magnitude of, or this distance gives you the magnitude of the driving force required for mass transfer. So if the intersection point is moving closer to the equilibrium curve, this distance is decreasing. That means the magnitude of the driving force for mass transfer is decreasing, and therefore you need higher number of stages to bring about the desired separation. So with a decrease in the magnitude of the driving force, the number of stages required for the desired separation, it increases. And therefore, a taller column will be required to accommodate those increased number of stages. And you have, when you are decreasing the reflux ratio, that is, you are decreasing reflux to the column, then a lesser quantity of liquid will be flowing down to the reboiler, and it will be boiled to produce a lesser quantity of vapor, which will be rising to the top, and then this lesser quantity of vapor will be taken to the condenser, and it will be condensed in the condenser. That means the conclusion is, with decreasing reflux ratio, a lesser quantity of vapor is required to be condensed in the condenser. That means the condenser heat duty, it decreases. Okay, so as I said earlier, a lesser quantity of liquid has to be boiled in the reboiler, which means that the reboiler heat duty also decreases. Okay, so with decrease in the reflux ratio, there is decrease in the magnitude of the driving force because the two operating lines are moving closer to the equilibrium curve, and due to decrease in the magnitude of the driving force, the number of stages required for the desired separation, it increases. Therefore, a taller column is required. Then, since a lesser quantity of vapor is required to be condensed in the condenser heat duty decreases. Similarly, a lesser quantity of liquid is required to be boiled in the reboiler duty also decreases. Okay. Now, if you go on decreasing the reflux ratio further, what will happen? A further decrease in reflux ratio, it causes the intersection of the two operating lines on the equilibrium curve. So if you go on doing decreasing the reflux ratio, what can happen? This intersection point will occur on the equilibrium curve. And when this happens, the reflux ratio cannot be reduced further. And then that reflux ratio is the minimum reflux ratio. So when you have minimum reflux ratio, or when the operating lines intersect on the equilibrium curve, then you cannot decrease the reflux ratio beyond that point. Then you have what is called the minimum reflux ratio. Okay? So now the lines, they are going to intersect on the equilibrium curve. Intersection point of all the three lines, or the three lines are meeting at a point that is lying on the equilibrium curve. Okay, so as the reflux ratio becomes minimum, or at the minimum reflux ratio, the operating lines intersect on the equilibrium curve, as you can see in this diagram. Their intersection is occurring on the equilibrium curve. Therefore, the driving force for mass transfer, it becomes zero. Why? Because the distance between the operating lines and the equilibrium curve along the Q line, it has become zero. And this distance is nothing but the magnitude of driving force. So when the intersection is on the equilibrium curve, then driving force for mass transfer is zero. And therefore, an infinite number of stages are required to bring about the desired separation. So with this case where the driving force for mass transfer is zero, you will need an infinite number of stages to bring about the desired separation. And an infinitely tall tower will be required to accommodate this infinite number of stages. Then, as far as condenser is concerned, minimum quantity of vapors will be going to it, and they will be condensed in the condenser. Therefore, minimum amount of heat will have to be removed, and therefore, for condenser, heat duty is minimum. In the case of reboiler, minimum quantity of liquid will be going to it. Minimum quantity of liquid will be boiled in it. Therefore, minimum amount of heat will have to be supplied in the reboiler. And that's why heat duty for the reboiler is also minimum. In short, with minimum reflux ratio, heat duties for the condenser and the reboiler, they are minimum. Okay, now the other important task is how to find the minimum reflux ratio. Now we have understood what is minimum reflux ratio, what happens when you operate the column under minimum reflux ratio. So let us understand. Now let us know how to find the value of minimum reflux ratio. Okay, so for that we are going to use this diagram. So you have, in this diagram, you have a condition where the two operating lines are intersecting on the equilibrium curve. That means the reflux ratio in this case is minimum. Okay, so I'm going to name this point as point M, and coordinates of this point let they be x star and y star. That means x coordinate is x star and the y coordinate is y star. Okay, then you have one more point over here which has coordinates of xd, xt. So this point, let me call this point as P. For our understanding, let us call it as P. And this point P, it has coordinates of xd, xt. Okay, so with this understanding, let us first, this y coordinate of this point is also xt. So with this understanding, let us first know what is the geometrical, how to get the geometrical slope for the rectifying section line. So this is point P, and point P I'll write over here. You have point P which has coordinates of xd, xd, and then you have another point M which has coordinates of x star and y star. Okay, now we are trying to get the geometrical slope. So geometrical slope will be simply given by this equation. I am denoting it as ESG. So this is y star minus xd, y star minus xd. Or to understand it in a better way, what I will do, I will interchange the positions of the 2 points. So I'll first write M which has coordinates of x star, y star, and then you have point P, which has coordinates of xt, xt. Okay, so geometrical slope will be y star minus xd divided by x star minus xt. Now, you also know the slope of the rectifying section line in terms of r. It is given by this section, this equation, sorry. SR is equal to r upon r plus 1. So, if these two slopes, slope in terms of r and the geometrical slope, they are equal, that means r is having its minimum value. That is, it is minimum reflux ratio. So, if Sg is equal to SR, that means R is equal to R minimum. That means when you are at a point on the equilibrium curve, then the reflux ratio is minimum. So, simply if Sg geometrical slope is equal to slope in terms of R, then R must be equal to R minimum. So, if I use that, I will be getting this equation y star minus xd. I am equating the right hand sides of the two equations. So, y star minus xd divided by x star minus xd is equal to R minimum upon R minimum plus 1. So, I will simplify it further. So, previously we got this equation y star minus xd upon x star minus xd, that is equal to R minimum divided by R minimum plus 1. I will take reciprocal on both the sides. So, it will be x star minus xd divided by y star minus xd is equal to R minimum plus 1 upon R minimum. In the next step, what I will do, x star minus xd upon y star minus xd, that is equal to R minimum upon R minimum plus 1 upon R minimum. That is, I have separated the denominator. So, in the next step, it will be asked x star minus xd divided by y star minus xd, that is equal to 1 plus 1 upon R minimum, because R minimum upon R minimum is 1. So, that is x star minus xd divided by y star minus xd is minus 1 when I bring this 1 on this side. So, minus 1, that is equal to 1 upon R minimum. Let us simplify it further. So, previously we got this x star minus xd upon y star minus xd minus 1, that is equal to 1 upon R minimum. Now, I will simplify the left hand side. So, it will be x star minus xd minus y star plus xd divided by y star minus xd, that is equal to 1 upon R minimum. And in the next step, xd and xd will get cancelled out, and you are left with x star minus y star divided by y star minus xd, that is equal to 1 upon R minimum. That is, R minimum is equal to y star minus xd upon x star minus y star. So, if I take reciprocal on both the sides, I will be getting the final equation. And then I can rearrange it in a different way. And I can write it like this. R minimum is equal to xd minus y star divided by y star minus x star. So, this equation will help you to get the minimum reflux ratio. So, with this, I end my discussion for the topic of minimum reflux ratio. So, here I have discussed what is the concept of minimum reflux ratio, what changes occur when the column is operating with minimum reflux ratio, and finally I have told you how you can get the value of minimum reflux ratio. So, you just simply have to get this point, and if you think it in a different way, you can just see, if you are able to draw the Q line, you will be getting this point. There is no need of drawing all the three lines. You simply draw the Q line and get the point where it intersects the equilibrium curve. That will be the same point through which the two operating lines will be passing when the reflux ratio is minimum reflux ratio. Okay, so with this, I end my discussion for today. I hope you have understood the concept. If you have any doubts, please mention them in the comment section. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. And for now, have a nice day and hope to see you soon in my next video.